I think we can start the class today. So let me recall what we were doing. We were talking about linear codes. So what is a linear code? C is a k-dimensional subspace of FQN is called as a linear code, and the parameters are defined as n, k, and d. This is query code, where n is the length, k is the dimension, and d is the minimum Hamming distance. Okay. Now a code can be specified by a linear code can be specified by two things, two matrices. One of them is known as generator matrix, right? And so C can be specified its span of G over FQ. G is known as generator matrix. G is your K cross N matrix consisting of basis vectors. And standard form for G is IK and A for some matrix A. IK is the identity matrix of size K by K. This is K cross N. C can also be specified by another matrix known as parity check matrix. Which is a matrix of size n minus k cross n. Okay, n minus k rows and line is. G is given by ik bar a, h is given by minus a transpose slash I n minus k. We have seen this formula in the last class. Given generator matrix in this form, parity check matrix can be given like this. So this is n minus k cross n, that is the size of h. Now you can immediately note one of the so basic definition of h is C is nothing but all the vectors of x is equal to x1, x2, xn such that hx transpose is equal to 0. That is our C. Nothing but the null space of the matrix H. From the point of view of linear algebra, you know. Third property that one can observe is that GH transpose is equal to 0, which is clear, you know. When you multiply, you know, GH transpose, it turns out to be a 0 null matrix. Okay, so this motivates us to think that probably G and H are dual space, and so we define what is known as inner product. Inner product. On this space FQN, we can define inner product as if there are two vectors x and y in FQN, you know, I can define the inner product between them as x1 y1 plus x2 y2 plus dot 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 xn yn. This is your inner product. Okay, so let us take an example. You know, if we take f Q as 2 binary and say F2 4, and if I take two vectors X as 1 0 0 1 and Y as 1 1 0 1, what is the inner product? X dot Y. We can also write X dot Y, same thing as X dot Y, or this quantity. Inner product X dot Y is this into this, 1 into 1 plus 0 into 1 plus 0 into 0. So 1 into 1 plus 0 into 1 plus 0 into 0 plus 1 into 1. Now this is plus 1, which is 2. 2 is nothing but 0 mod 2, because Q is 2 here, right? So mod 2. So inner product is 0. So these two vectors are nothing but orthogonal actually. Okay. So we can say that X is perpendicular to Y, orthogonal. Orthogonal to Y. It is orthogonal to the vector Y. Okay, so let us take another example. If X is 1 1 1 1 and Y is 1 1 1 0, so the inner product X dot Y will be 1. You can compute it directly. Okay. So inner product satisfies certain basic properties, which I am just mentioning. I mean, I can call it as a lemma. Nice lemma, simple lemma. For any three vectors, suppose we have any three vectors u, v, and w in fqn, and suppose lambda and mu are scalars in fq. Okay, then first thing, inner product of u dot v is same thing as inner product of v dot u, right? V dot u. And second property, that lambda times u plus mu times v dot w is equal to lambda times u dot w plus mu v dot w. So this is another important property. Now I can define, so if C is a, in, so suppose C nkd, then I can define this dual code. Okay, dual code can be defined as C per, defined as C per as set of all those vectors y in fqn such that inner product of x dot y is equal to 0 for all x in C. Okay, so this is known as null space of C or dual space of C. Okay, so we call it as dual code. Dual code of C. Sorry, null, not null space, but dual code of C. So there are actually some properties here which I would like to mention. First thing, in fact, some definitions here. First definition: if C is a subset of C per, we call it as self-orthogonal. And C is called as self-orthogonal code. Second, if C is equal to C per, it may happen that C is equal to C per, then C is known as self-dual code. Okay, C is known as self-dual code. So let us take some examples. Suppose Q is Q is, and so we are looking at Z2 raised to power 4, and suppose C is 1 2 3 4 1 1 0 0 0 0 1 1 1 1 1 1. So I can see that perp turns out to be same thing as C. This is self-dual code. Okay. So let us take another example. If C is 0 0 0 1 1 0 0 1 1 1 1, right? This is subspace of Z2 raised to power 3. So I can list all the vectors here. Clear to you: 0 0 0 0 0 1 0 1 0 1 0 0, right? Then 0 1 0 1 1 1 1 0 1 1 1. If our full space is this, C is this, what is C per? Let me actually compute it in front of you. So I will check the first vector 0 0 0 of inner product of 0 0 0 with all the vectors will be 0 anyway, right? So C perf will have 0 0 0, right? Now if you take the other vector 0 0 1, this will not give you, this is not orthogonal to any vector in C. So 0 0 1 is not give you the answer. Okay, I mean it's not, it should be orthogonal to every element in C. 0 1 0 is also not orthogonal to every element in C. 1 0 0, if we try 1 0 0, it is also not orthogonal. 1 0 1 is also not orthogonal. 0 1 1 is also not orthogonal. 1 1 0 is also not orthogonal, to every element. Only thing left is 1 1 1. If you take 1 1 1, it is inner product with 0 0 0 is 0. Okay, with 1 1 0 is 0, with 0 1 1 is 0, and 1 0 1 is 0. So C perp is 1 1 1, another vector. Okay. So this is our dual code. Okay. Now some important properties. What is the dimension of C perp? It turns out that dimension of C perp is n minus k. So if dimension, and we know that dimension of C is k, so we have this property that dimension of C plus dimension of C perp is nothing but n. The dimension of, okay, this is the dimension. So second property that I would like to mention, C perp is again C itself. I think this is an easy property. One can prove it. That C perp is nothing but C. Okay. So the dual code, this is how we define dual code. And actually you can see that self-dual code and self-orthogonal codes are two important properties actually. Okay. Self-orthogonal and self-dual. C is said to be self-dual code if C is equal to C perp. C is said to be self-orthogonal if C is subset of C perp. Okay. Okay. Now keeping this in mind, now we can see some more properties. Now it turns out that because GS transpose is equal to 0, it turns out that dual code has generator matrix H. Okay. So some properties of the parity check matrix PCM. First lemma, or I would call it as a theorem, any d minus 1 column of H, H is your n minus k cross n, are linearly independent. This is a very important property, that any d minus 1 column of H are linearly independent. So what I'm saying that if C is your NKD code, so we have C is our NKD code. So the minimum distance of C is D, right? So let us write down the parity check matrix as first column, second column, third column, HN, right? This is our parity check matrix. N minus K cross N. N minus K rows. So the length of each column is N minus K, and total number of columns. Now we know that C is nothing but all those vectors X in the whole space FQN such that Hx transpose is equal to 0 by definition of the parity check matrix type. This is the null space of H. Now we have to show that any d minus, suppose, so the proof goes like this. Suppose d minus 1 columns are linearly dependent. So they are linearly dependent. That means there exist scalars x1, x2, xn such that d minus 1 of them are non-zero, right? Where x1 h1 plus x2 h2 plus dot xn h. X is not all of them zero, so d minus 1 of them are non-zero, right? So their combination is 0, where d minus 1 of them are non-zero. So that means this is nothing but, this implies that exists a vector x equal to x1, x2, xn in C of weight t minus 1, right? So we have assumed minus 1 columns of H are linearly dependent, and that means exist these scalars x1, x2, xn such that the linear combination with the columns is equal to 0. And these are such that d minus 1 of them are non-zero. That means there exists a vector x1, x2, xn in C such of weight d minus 1. Right. Now this is a contradiction. This is a contradiction. Why? Because weight of x is at least d for any x in C. If you take any vector x in C, the weight of x will be at d. And here getting a vector less than d, which is d minus 1. So this is a contradiction. So d minus 1 columns are linearly independent. This implies that any d minus 1 columns are linearly independent. So this is a nice that d minus 1 columns of H are linearly dependent. Okay. Now we come to another property which is pretty nice, and we call it syndrome. Syndrome. Suppose x is a vector from which is sent, okay, and y is received vector. So obviously y will be x plus e, where e is an error vector which is added. Is an error vector. Is an, okay. Now, basically, syndrome of y C vector is defined as H transpose. So we compute syndrome. So this is a column vector S1, S2, Sn minus k, and minus k cross 1. This is syndrome. Okay. So there are certain properties of the syndrome, I should say. First property is known as syndrome. This means symptoms of errors, syndrome here, syndrome of receipt vector. First, syndrome of y is 0 if and only if y is a code word in C. Right? Now this is true because if y is a code word of C, that means H5 transpose is equal to 0 anyway, right? So syndrome will be 0, right? By definition of the code, right? And it turns out to be y has to be a code word of C. This is very straightforward property. Second property, can form a coset decomposition of C from C, coset decomposition. So we have a very interesting property about the cosets, which says that two vectors are in same coset of C if and only if they have the same syndrome. The two syndrome. The proof is really straightforward. If U and V are in same coset, two vectors are in same coset, this implies if and only if this U plus C is same thing as V plus C, right? It will be, cosets will be same. And this is true if and only if U minus V belongs to C by definition. If this implies that H of U minus V transpose is equal to 0, if only if this means HU transpose the same thing as HV transpose. That means syndrome of U is same thing as syndrome of V. So basically, if two vectors are in the same cosets, they have the same syndrome. I can compute the syndrome and I will get the same syndrome, right? Okay. So let us look at our previous example that we so basically last property I can, there is one-to-one correspondence between coset and syndrome. Okay. Now an example. Our generator matrix is 1 0 1 1 0 1 0 1. This is 2 cross 4. Parity check matrix is 1 0 1 0 1 0 1 2 cross 4. C is our 4. Okay. So I can form the C. So basically C will be forwards 0 0 0 0 1 and finally 1 1 1 0. Okay. Okay. So we can suppose from this we can form the cosets. So I can just mention code 0 0 0 0 1 0 1 1 0 1 0 1 1 1 1 0. The first coset that we can make is 1 0 0 0 0 0 1 1 1 1 0 1 and 0 1 1 0 set 0 1 0 0 1 1 1 1 0 0 0 1 1 0 1 0. Next 0 0 1 0 1 0 0 1 0 1 1 1 1 1 0 0. So I can compute the syndrome of each vector. So syndrome of any vector in C will be 0 0 column. For the second one it is 1 1. For the third one it is 0 1, and for the fourth one it is 1 0. In fact, I can write down the message as 0 0 1 0 0 1 1 1. So this is your message actually. Okay, so this is our coset decomposition. Now you see syndrome of any vector in the same coset is same actually, no matter what you do, and it is 0 if it is a code word. Okay, so now let us see how it is used to decode the code. Suppose received vector is y is equal to 1 1. We compute the syndrome of y turns out to be 0 1, which is this syndrome. Okay, if syndrome is this, okay, so that means the error vector is this. Okay, so that means error vector E is coset leader 0 1 0 0 is our error vector. So actually the code word X that was sent was 1 1 1 1 minus 0 1 0 0, and that turns out to be 1 0 1 1. This was the actual vector sent. So message will be, if 1 0 1 1 is a message, also what will be 1 0. So this is how we decode. Okay, so we take the C, form the array decoding, compute the syndrome. So actually, syndrome is enough. We don't have to form the coset now. Y is received, compute the syndrome, and then actually, if syndrome is this, we know the coset leader. Okay, we subtract the coset leader, we know the answer. Now, actually, in case binary codes, there is much more better way of decoding. Let me explain to you what is that. First of all, this property about the, for the binary codes, what happens? Okay, so if y is vector is x plus error vector e, right, where x belongs to x code word, y is a received vector. Syndrome of y will be, syndrome of y is nothing but hy transpose, which can be written as h x transpose plus h e transpose. E is the error vector. Now x transpose is equal to 0 because x belongs to C. So we are left with syndrome of y. The seed vector is nothing but he transpose. This is a nice thing, right? Now, if in the binary case, suppose error vector is something like this, 0 0 and 1 0 0 1 0 0 1 0. Suppose at three places A, B, and C we have ones. So that means, and H is H1, H2, Hn. Then in that case, syndrome of y is nothing but summation over I, Ei. That means it is sum of the columns HA plus HB plus HC, where the syndrome is non-zero. So this is nothing but, this is a very interesting property. Syndrome for binary case. And this is something to keep in. For binary case, syndrome is equal to the sum of the columns where error occurred. Okay, so this is a nice property about the syndrome. In the binary case, syndrome is nothing the sum of the columns where the error occurred. So essentially, we will see later on that for the Hamming code, actually, this property is really useful because Hamming code is a singular error correcting. So syndrome gives you the column, actually, where the error occurs. So the position. So decoding is really straightforward. You just compute the syndrome, see which column of the parity check matrix you arrive at, and just flip that bit in case of binary, right? And errors are corrected. It's really powerful technique. So we will see that how this can be used. Okay. So this is all about syndrome decoding. Any question at this point?
No, sir.
Okay. Okay, so I think fine. This is all about syndrome decoding, and some idea about parity check matrix, and I mean, these are the really very basic things. I think anyway, I think I'll stop at this point because this is one topic is finished. So in the next class we can start the next topic, which is the Hamming code. So if you don't have any questions, so this is all for today. Okay. So I hope you got the idea about the syndrome. Okay. How the decoding is done with the syndrome business. Okay. So this is very, very important. We'll show you how in the properties of the parity check matrix, we can do wonders in case of codes. So in the next class, I am going to construct the Hamming code using parity check matrix. It's a beautiful construction. We'll talk about that, and then we will see the dual code, which is a simplex code. Okay. So what is the connection between Hamming code and dual code? Hamming code and simplex code. They are dual to each other. Okay. And I think first we'll discuss the binary case, and then we can talk about the higher order case. I think I have already seen you the assignments. Now it's time for you to do the assignments. Okay. And for today, so this is a really important thing about the linear codes. You should know about the generator matrix. You should know the parity check matrix. Okay. You should have an idea of what we learned today is the inner product, syndrome calculation, and array decoding or quotient decomposition with help of syndrome, and also the key idea that in the binary case, syndrome of a received vector is nothing but some of the positions of columns where the error in the in the received vector. Okay, so this is that's all about the linear course today. So next class we'll compute we'll discuss the construction of new codes such as Hamming code. Then we'll construct the Gole code, Reed-Muller code, Reed-Muller code later on. And many other things. Thank you.